So, we will move on to the other interesting physics in consumable welding process, which is metal transfer. So, I showed you a video in earlier classes. So, in a GMAW you melt and the droplet is getting transferred to the workpiece. How does the droplet get detached and then transferred to the workpiece? Why should it do? Gravity. Is only gravity? EMF. Okay, so first we will take gravity. How would gravity assist the droplet transfer? Would it always assist the transfer, droplet detachment, or it can also resist the detach? It's always assist, all the cases. Yeah, it based on the welding position. If it is downhand welding, it always assists, isn't it? If you are doing uphand welding, gravity will not assist the droplet transfer. It is depending on the position of the welding, right? It's clear. I will show you a video and then we will come back to that. So, previously we saw one video. So, in this case I showed you a video of two cases, this wire and the other wire. This wire droplet transfer is much different. So, when it is getting transferred, it is transferred into a stream like opening a tap, whereas in this case it is transferred as a globes, isn't it, as a ball. Why would they change? Right? Why would they change? Depending on the current. How does only the current is going to change the transfer? So, what are other forces which can influence? So, I have an analogy here, bubble. Okay, so let's, I hope all of you played with bubble, right? So, I am going to blow a bubble. Okay. Now, if I want to detach this bubble from the tape, what are the forces that are involved in this detachment when the droplet is detached from this bubble? Which force would assist, which force would resist the detachment? You said gravity. How does gravity influence? Suppose I am doing it here. Okay, if I do it like this, I already changed the diameter of the bubble. By doing some way, some trick, in first case the diameter was bigger, in the other case diameter was smaller. Why would that? Which force? Which force? So, first gravity you said, right. So, gravity now is promoting the detachment. Suppose if I am doing it like this, it is still getting detached, even though gravity is opposing detachment, isn't it? So, something else is playing around. The one force is the blow I do. Okay. So, you can call that blow, what do you call that blow? Aerodynamic force, okay, some force. Right, that is there. So, the blow I do, it always assists the detachment, because the faster I blow, the bubble can separate from these the point of generation much faster and smaller diameter, isn't it? What are other forces you can think about? Surface tension. Okay. How does surface tension help? Will it help in detachment or it resist? What happens to surface tension? Will it assist the detachment? It will always resist, because that is the role of surface tension. It has to reduce the surface area. So, it would never allow the droplet to detach. If it detaches, then surface area increases. Okay, the surface tension would always oppose the detachment, isn't it? What are other forces you can think about it? Lorentz force. Okay, so it is there, independent of Lorentz force. No current here, right? I am not blowing anything, isn't it? Unless I have an like an X-man or so, I can send some electrons whenever I blow, then I will be very rich. Suppose I am blowing against wind. Now imagine there is an air, isn't it? Air pressure is there. Suppose there is a fan, I am blowing against a fan. What force you would generate? So when the bubble is going out of this mouth to outside, there is also something which is resisting.
Air pressure.
Yeah, air pressure, isn't it? So the air pressure would always push, because you are working against the air pressure, isn't it? That means that the air pressure, you can also say that suppose I am blowing against an air conditioner. So that always push the droplet to be it in its position, right. So you can say it is a vapor pressure. So now, so we have a gravity, aerodynamic force. So aerodynamic force is my blow, and then surface tension, it is the bubble, the composition material, and then vapor pressure, it is atmosphere. So in a welding case, of course we also have a current. Okay, so you will also have a Lorentz force. So Lorentz force, so this force gravity based on the location, whether you are doing in down hand welding or up hand welding. So the G is a function of theta, cos theta, right. So G cos theta, right, with respect to the your work piece. If it is 90 degree, G is maximum, right. If it is 0, it would resist, right. The aerodynamic force is the blow force. In welding case, aerodynamic force is a plasma jet force, plasma jet velocity, right. So that is what is blowing the droplet. So like I did it in my bubble, the faster or the heavier I blow, droplet can be attached with smaller diameter. Same with the plasma jet as well, it will always assist the droplet detachment. So the plasma jet would also assist the droplet detachment. That is aerodynamic or plasma jet force. Then surface tension, again it is a material specific, right. So it would always resist the detachment. The vapor pressure, why do we have vapor pressure during welding? So during welding we also create the metal vapors, it would be going up, isn't it? The melt pool vaporizes, it goes up, it will always push the droplet to be in its position. Same in the bubble, suppose I am blowing here, so if you have wind is coming, right, the droplet would be attached, isn't it? So the vapor pressure which is coming from the melt pool would always resist the detachment, right. And then we also have a Lorentz force. Lorentz force is slightly complicated, that is based on the shape of the arc. Okay, so if arc is very wide, suppose if you have a tip like this and you have a droplet formed, if the arc is like this, the electrons would be diverging when they are travelling. If this is the case, so then droplet detachment is promoted, because the electrons would diverge by pushing the droplet out. So, imagine now the arc is very narrow. Okay. So, arc is narrow. In this case, your droplet diameter is already larger than your weld, the electrode, as well as the arc is in very narrow. In this case, the electrons will converge, is not it? Because obviously electrons would travel via arc, sustained discharge, recall. If your arc envelope is very narrow, you have a convergence of the tiny particles. The Lorentz force would be converging. In this case, these particles or these Lorentz force would resist the detachment, is not it? If it is diverging, it can take the droplet, it is diverging, but they are converging, that means that the force would be keeping the droplet in its place, right. So, the balancing these 5 forces would determine the transfer kinetics as well as the shape of the droplet, right. It is clear. So, these 5 forces, how it is balanced? The forces which are going to assist the droplet transfer, the forces which are going to resist the droplet transfer, right. If they are perfectly balanced, system is in equilibrium. Okay. In order for droplet to be transferred, one of the forces which assist should be maximized, right, either gravity or vapor jet. Vapor jet means the plasma jet, the aerodynamic force or Lorentz force. One of them should be maximized to overcome the resisting forces. Okay. So, we will see the force balance, and that will determine the shape as well as the transfer kinetics, number of droplet transferred per unit time. Yes, is clear. So, that is what he said, forces in the metal transfer, they are gravitational force, right. The gravitational force determined by the angle cos theta, whether you are doing a downhand welding or uphand welding. If you are doing a downhand, it is always assist the droplet transfer. And then you have a plasma jet or aerodynamic drag, FD, and then electromagnetic forces. So, most of the cases Lorentz force always assist, because creating a narrow arc is very difficult. Okay. So, you always have a droplet diameter much smaller than the arc envelope diameter. So, you always see that Lorentz force aids the droplet detachment, right. So, these 3 forces, Fd plus Fem and Fg, if it is equal to the vapor jet plus surface tension, it is an equilibrium situation, right. So, if the droplet should be detached, either G must be, the force, gravitational force must be higher, and this is fixed, that is the process parameter, right. And then Lorentz force, it is function of current. So, what current are you operating? So, in this case, suppose if you want to detach a droplet, so either your gravity should assist or your Lorentz force should assist, right, to overcome the forces that are resisting the droplet detachment, which are vapor jet force and surface tension force. Yes, it is clear. So, how does the gravity work? So, this is the force balance I was talking about. So, you have a droplet, the vapor jet force is coming from the vapor, Fv. So, they will always come from the workpiece towards the droplet. So, the force would always resist. The surface tension would keep the droplet in its position, is not it? So, it would not allow droplet to detach because you are creating new surface area, right. So, these two forces would always oppose, right, and then gravity, if it is down and welding, would act to assist the droplet detachment. Similarly, plasma drag force, which is my blow. In arc, it is a plasma jet, would always assist the droplet detachment, and then you have Lorentz force. If the Lorentz force is always diverging, it will always assist the detachment, right. It is clear. So, if in this equation, so this is material parameter, this is in a way material parameter, is not it, the vapor generation, and this is process parameter. So, now the two things we can independently change is gravity, which it cannot be changed, but the force can be manipulated by changing the mass, is not it. So, mg, or you can change the current, right. So, we look at independently now each equation, then we can understand how the droplet shape can be changed as a function of these parameter, right, current as well as the droplet size. So, gravity, so this is what, 4 by 3 pi r cube, volume times density, it is mass, is not it. Suppose if you are operating very low current, extremely low current, there is no influence of Lorentz force, right. So, then if you want to detach a droplet, you need to maximize the mass, so that droplet can be detached, right. So, now we already see the video, I showed you two videos. So, one of the wires, it was transferring as a globes, individual globes. So, why are they doing it? Because in that case we intentionally kept the current extremely low, so that droplet detachment is seen as a globes which is assisted by the gravity, is not it. So, the moment the droplet reaches a critical mass, if Lorentz force is very low, the current is very low, the droplet can be detached by the gravitational force. That is why when you are welding at very low currents, you always see globular transfer. The transfer happens as the globes. That is because the main force which assists the droplet transfer is gravity, right. So, that is what is known as a globular transfer, we will see in subsequent slides very clearly. So, when at the low current, when the Lorentz force is not maximized, so the maximum force that influence the droplet detachment is a gravity. Gravity is influenced by mass. So, in order to achieve the droplet transfer, the droplet should reach critical mass, then it can be transferred. Yes, it is clear. So, the term here is cos theta. So, this is a very significant force when you are doing it in low current. So, for 1.6 mm diameter in argon low current, so it can be say 260 to 600 10 power minus 5 Newton the force. Yes, it is clear. So, 1.6 mm it is coming around 600 times 10 power minus 5 Newton. So, for when the Lorentz force is very small at lower currents, the gravity is the main force which would detach the droplet. That is why at lower currents you see globular transfer, because the droplet has to grow in its size to attain the critical mass, and then it can drop, right. It is clear. So, now the other force, the aerodynamic force or plasma drag force, it is depending on the gas velocity and density of the gas, and of course, the drag coefficients. So, when you are using convective gas for example. So, you can have a very high plasma jet velocity created. So, that means that in that case the droplet diameter will be much smaller when it is detached. Okay. So, in that case the process, the shielding gas can also influence your droplet detachment. For example, for a same current, same the material chemistry, if you change the shielding gas, your plasma jet velocity can also change. If that is the case, then FD can also influence the droplet detachment, right? It's clear? Yes or no? So, plasma jet force for a given process, given shielding condition is fixed, it cannot change, right, because it is a function of a shielding gas, okay, the velocity as well as the density of the gas, right, is clear. And if you keep all the parameters constant, if you change the shielding gas, then you will see the effect of the shielding gas on the droplet transfer, because the drag force will change. Yes, clear? Yes, okay, good. And this force, like it's a blow force, like I did it when I was detaching droplet. If I blow faster, I would detach the smaller droplets. If I blow slowly, the force is getting balanced, so droplets can grow. So, now the angle is 45 degree. If you are doing like this, if you are doing it different. So, now the angle is 45, so cos 45. So, gravity influence is negligible. So, my drag force, aerodynamic force, it has to overcome the surface tension. Okay. So, if surface tension is maximized, droplet cannot be detached, it will grow, isn't it? If I am doing very slowly, the surface tension is keeping the droplet in its position. So, my drag force is not overcoming surface tension force, so droplet is not detached, isn't it? So, droplet is growing in size. Suddenly, if I tilt my head, you may see droplet detaching because gravity would assist. You want to try? Okay, so but then the force balancing will be very tricky. I will have to make sure that when I am going like that and doing like this, the drag force would be same. It is very tricky. Let us see. So, I need to overcome the surface tension, right? No. So, drag force is the now overcoming the surface tension. See, already droplet diameter is decreasing, isn't it? So, if you want to make a bigger bubble, you need to blow like this, okay? It is already there. I am running out of breath. So, my drag force is decreasing. So, you can play around. So, based on the gravity, the drag force, the balancing force is surface tension. So, I need to overcome the surface tension to get the bubbles to detach from the whatever instrument, right? It is clear. The same thing over here also, the plasma drag force, if I am blowing really fast, the bubbles can be detached much faster, right? It is clear. So, then the drag force overcomes, that becomes the rate controlling than gravity, right? It is clear? Good. So, the third force which assists is Lorentz force. So, again you can use the equation to calculate. So, this is magnetic permeability, and this is exist under the entry radius. So, R is entry radius for example. So, this is wire, okay, and then you have a droplet formed and something like this arc. The ratio between the radius, between these radius, right. So, if RA is bigger than R, your Lorentz force would assist the droplet detachment, isn't it? Because then the fundamental, what is Lorentz force? The Lorentz force is force generated between the basic particles of electrons and ions. Okay, so when you keep it closer to each other, then you create enormous amount of Lorentz force, and then how the particle would travel. If they are diverging, for example, in this case, so obviously the electrons which are generated which diverge in the R column. That means that while diverging, they can assist the droplet to detach from the tip. So suppose if RA is different. Now RA is smaller than your R. So now in this case RA. So if R is smaller than R, then these electron particles would try to converge, isn't it? So this term becomes smaller. So obviously then what will happen? If they are trying to converge, they would not assist the droplet transfer, right? So they would try to shrink the droplet, right? So they would try to, because it is a bubble is there and the force is pulling the droplet, so they would resist the droplet transfer. See, in most of the welding case, our arc diameter or arc envelope diameter will be much larger than your droplet diameter. So you always have a situation where your arc would be much larger than your filler wire. So in that case, your Lorentz force would always assist the droplet detachment, and this becomes very significant when you increase the current. Okay, so when the current is increased, Lorentz force becomes highly significant. That droplet can be attached with smaller mass. Okay, because plasma drag force is a function of your sealing gas, your gas velocity. For a given process condition, it is fixed, right? So suppose if you want to minimize the droplet diameter, what we do? High current. So the Lorentz force can detach the droplet with much finer diameter, right? So in the video I showed you two conditions, same wire, everything is fixed. So this wire, the welding is done with low current. In this wire, welding is done with high current. You see already influence. In low current case, droplet is detached after achieving a critical mass, whereas in this case, the droplet diameter is much smaller, isn't it? It is like a spray. The droplets are transferred and continuous drops. So the drops overlap, it becomes stream or spray, we call it. So in this transfer we call it globular transfer, whereas in here we call it spray transfer, because the drops are all accumulated and becomes continuous spray. Yes, it's clear? So these three forces would always assist. Gravity, again, assume that we always do downhand welding, right? It's clear? So the Lorentz force, that as I explained. So if your exit radius is smaller than entry radius, it would always resist. That means that arc is very narrow. The electrons would converge, they will not diverge. So in this case, the exit radius RA is larger than the entry radius. That means it will diverge. Okay, if you increase the current further, so you also increase the arc envelope. That means that the droplet can be detached with very small diameter, right? You have maximum divergence, and this situation can also happen. So when you are increasing the mass significantly, then you also have a diverging path, even if arc a converging path even if arc diameter is arc envelope is larger. So, we will see in subsequent transfer case how will that happen. So, in most of the cases in a welding case based on the nature of the Lorentz force convergence and divergence. Okay. So, if your arc envelope is very narrow and if the exit path is narrower than your entry path, then the Lorentz force would resist. That is highly unlikely in arc welding case. In most of the arc welding case, this is the situation, and if you increase the current, this becomes like that. Yes, it's clear? Good. Any questions so far? Yes or no? Nope. Good. Again, two forces would oppose, and these two forces should always be overcome if you want to do welding. Otherwise, there is no GMAW, isn't it? Droplet will not transfer. The two forces would resist the droplet transfer or vapor jet force and surface tension. And if you are not overcoming, then you can't weld, right. So, the vapor jet force is coming from the vaporization of the metal. Okay. So, the mass vaporized per second for a given current and the current density and the vapor density. So, vapor jet force would always oppose the droplet detachment, and we can calculate, right. And then the last force, surface tension. Surface tension again the function of composition, right. So, diameter, you can calculate the surface tension of the molten droplet from the droplet diameter, and this function, this is the coefficient of surface tension, and then you have the capillary actions, that is determining the surface tension, right. It strongly depends on composition, because if you change the composition, surface tension also change, right. So, suppose if you want to transfer droplet with lower surface tension, then you need to add some elements. Okay. So, you can enable or you can assist the droplet transfer by adding fluxes. Okay. So, in MMAW or flux core arc welding, we add fluxes, so that you can play around the surface tension of the droplet can be detached at low current. Okay. So, that is the role of flux, to play around with the surface tension. If you look at all the values will be same except the Lorentz force. So, Lorentz force value can be very tricky. I do not know whether I have value. Yeah, see that 0.02 times I square. So, when the current is increased, the Lorentz force increase exponentially, right, whereas the other forces would remain in a similar amount, 10 power minus 5 Newton, right. It is clear? Good.